quick review here. On the monoatomic, you might remember that we mentioned both CV and CP. And maybe it's worth repeating again. I'll come over here to our little experiment that we've done a bunch of times. You can heat this gas up really in two different ways, actually more than two, but two we're going to focus on. If I clamp it and warm it up, that of course will warm up the gas to roughly 80 degrees Celsius. But I could also just as easily, let me cool it back down for a second, and have the clamp released, cool it down a little bit more, okay? I could also warm it up to 80 degrees with the clamp loose, so what we would call constant pressure, and of course as it goes up, it's pushing the environment back. And so I've said it a number of times, does it take the same amount of energy to warm it up in both cases? No, which would take more energy? Right, the constant pressure. The constant volume doesn't take as much energy because then all you're doing is making the molecules go faster. But when you have constant pressure and you allow that piston to move upward, then the energy you add not only makes the molecules go faster, but as you make them go faster, then they slow down again because they have to do work on the environment. They have to push that piston up. And so it's going to take more energy. And so where we left was this whole idea that CP should be greater than CV. And we did. And we saw this chart. We were partway through this chart. We had a CP here and a CV there. And we noticed that CP was greater than CV. In fact, we did the math on it here. Let's do the math again. If I was going to go calculate the total energy of a container filled with monoatomic molecules. And now, what do I mean by that word, monoatomic? Yeah, one single atom. If I grab my little box of atoms, if you could see it, it would look something like this. Helium, all the noble gases would be good examples of that. And what they can do is when you give them energy, all they can really do is move. Now they can move in the X or the Y or the Z direction. And so we said they had 3 degrees of freedom. And so you go to figure out how much energy it has, you realize that they have 3 times 1/2 kBT, right? That is where the energy would go as you are heating them up. There's only 3 places they can go: a movement in the X, a movement in the Y, a movement in the Z. If we multiplied that by N, then that would be, of course, the total energy of this container, N being the number of molecules in this container. If we then go to think about the first law of thermodynamics that says E equals Q plus W, and then when I realize that I warm it, say, at constant volume, then how much work is done at constant volume? 0. And so this internal energy becomes the same as the heat energy. And I think that's the easiest one. In fact, unfortunately, it's the one that people see right away, and I think that's why they have troubles with realizing that constant pressure takes more heat, or that adiabatic processes can change the temperature, because they only focus on just these two as being equivalent, the constant volume case here. But, well, I'll just come back here and finish the math. What we did last time before we left then is we said then this Q would be the same as the E, and so the internal energy being 3/2 Boltzmann's constant times its temperature times the number of molecules here. And then if we did a little substitution and replaced those two variables with number of moles times R, we could also write the internal energy, or the heat added at constant volume, like this. Then if we also realize that what we called the molar specific heat would be how much energy when you change the temperature, then we can write a change in temperature corresponding to a change in energy or a change in heat, so that the n's cancel off, the delta t's cancel off, and so we finished the day saying that for a single atom, a monoatomic gas, that the specific heat, the molar specific heat, should be 3/2 R. And sure enough, we got out the calculator and calculated that to be about 12.5. And so these experimental measured values do show that it comes out to be 12.5, kind of convincing us of our little model. And not perfect, obviously. There are some small subtleties there, but for, again, a first step, introductory thermodynamics, this gives us a nice conceptual picture of what's going on. In fact, we did one more step before we left here. We said, all right, if you know CV, you should be able to also find CP. You could really go through the same process. So if I kind of clear this area of the board and, well, I wonder if I can squeeze it in right here, because I would like to see it and compare and contrast with the diatomic here that we haven't done yet. But if I redo this row, it's going to be a little tight here, but E equals Q plus W. If we now take the pressure and hold the pressure constant, what's different in here? Well, this time there is a little bit of work, right? And so we would have E equals Q minus P delta V, where this P delta V is the work we get when we have constant pressure. Meaning then, as we move this to the other side of the equation, P delta V plus E is equal to Q. And that was our answer, that the Q here is going to be more than what we had before. Before we just had the E. And so, see if I can squeeze this in here. But this will be a P delta V. And in place of E, why don't I just put what we had before here, that this would be a N C V delta T equals Q. Now there's a very important subtlety I just did. Very powerful tool and often overlooked by students. What did I do here? Ah, good. Did you see that I just replaced E, energy, with a little equation that has constant volume? Is this a constant volume equation? It's not. So is this okay? Or is this invalid? Well, if you remember, we talked about the first law of thermodynamics. We said the Q depends on the path. It's path dependent, right? That's why we're going to see a CV is different than the CP. Fair enough? In other words, Q at constant volume would be this. Q at constant pressure would be this. Do you get the same Q at constant volume as constant pressure? No. You get the same amount of work at constant volume and constant pressure? No. But what did we say about the E, the internal energy? What's this? Yeah, state function, right? That was that magical word we said. We said, look, it doesn't matter what path you go under. And that's what I'm going to take advantage of. And then we're going to see that for the rest of the semester on the homework. And if you miss that, you'll not know where to go in a lot of problems. Or if you finally do look it up, you'll be questioning this same thing that hopefully you're questioning now. How come the solution manual, or how come the teacher used a CV? Isn't CV for constant volume? Sure, when applied to heat, right? because the amount of heat depends on what path you take. But E, if you know how to calculate E by any method, it's valid. You see that difference? This is a state function. And so I know the equation to calculate E with constant volume. I just derived it over here. Now, granted, I have a situation that I don't have constant volume, but could I still use it? Yes, that's the beauty of state functions. And so make sure you notice that and take advantage of that. And I didn't have time to emphasize that last time, or I kind of did, it was at the end, and I chose not to dwell on it. I go, you know what? This is too much for 2 hours into the lecture and people skip over this. So you got to see this. It's going to be real powerful. And when I do a bunch of examples for you, you're going to see me jump all over that. Because even though the process is not constant volume, I can still use it for the E. Can I use it for the Q? No. Can I use it for the E? Yes. Don't miss that. It's a state function. And so state functions versus the non-state functions, we got to pay attention to. And that's why we emphasized it earlier on here in our thermodynamics here. All right, so now knowing that, I can continue on, and in this step here, I can use the ideal gas law. Since we are dealing with constant pressure, PV equals to nRT would imply then that a P delta V would be an nR delta T. And so when you add that to nCV delta T, and then on this side of the equation for the Q, since we are dealing with constant pressure, we would have to use this side, not this one, but for the Q, we would have to use an nCP delta T. We see then that CP is really CV plus on R. And so CP is more than CV. How much more? By R. And again, if you look closely at these numbers as we wrapped up last time, if you take this CV and you add an R to it, you will get this 20.8. And they list it here as subtracting the two. And so there it is, the 8.31. And so CP and CV, or what's nice about it is they will always follow this pattern. CP will always be bigger than the CV, and CP will always be R bigger than CV.
So in that step here, the P delta V, you said you put here PV equals nRT. Right?
Oh, here? Yeah.
And then you said it makes, because of that equation, makes it equal to nR delta T. Is it because the delta V then moves on? Moves on to the T?
Okay, if I had a little change here,
right.
Since I have a constant pressure, the P can't change. So this side of the equation would be P delta V. And then what would change on this side of the equation would be temperature. So P delta V is the same as nRT. Okay? And I hope you're noticing the puzzle I'm beginning to set up. And that's really what I want to spend the day here, is do a bunch of these puzzles. Do examples for you. They get kind of tricky at times, and you got to see what path to take. And notice here that the path I take depends about, am I asking about Q or E? Or W? Is it constant volume? Is it constant pressure? Did I use the ideal gas law? Did I use the Molar specific heats? Right? And so kind of working through what the answer is going to be, it's this puzzle. Well, this can lead me to this, which can lead me to this, which I can do this. Oh, I can't do that this time, but you know, what's going on? And that's what I want you to see here with some examples that we're about to do. We finished on Thursday by actually putting this number in. We actually said, okay, the CV was 3/2 R, which we just got a few moments ago. You add it to the 1 R, and you are at 5/2 R. So CP should be 2.5 times R. And sure enough, 2.5 times R does come out to be 20.8. And so we see that CP is bigger. We see it's bigger by amount of R. We also see that the ratio of CP over CV, and I'll leave that one alone for a moment, but you see they did a ratio of it. And if I did that over here and wrote, okay, call gamma CP over CV, this would be 5/2 R over 3/2 R, which is what? R's cancel, halves cancel, so 5/3, which is 1 2/3. So 1.66 repeating forever and ever and ever. And at this point, you may not realize the advantage of the ratio of them, but that's the last step here in the chapter, that this ratio of CP of CV becomes important when we are working with an adiabatic process. Well, like I said, that's kind of a review, but I think a useful one to lead us into the problems here, because we did do the monoatomic gas. What would change then if I went diatomic? Yeah. Yeah. Because it has to do with temperature and work. And like I said, you're going to see it in the adiabatic process here in just a second. So let's move on to the diatomic. What would change here? Yeah, number of degrees of freedom. And you can see it right here. E would equal what? Well, I'll shut this one off a little bit. Sounds like a lot of you've already read this. That was good, because I heard 5/2. There's a little chart that your author did a good job of showing, if I can find the chart. This one here. And he simply says this: when you get to a diatomic gas, a gas that might look something like this, two hooked together like nitrogen, most of the air in front of us is nitrogen or oxygen, and it looks like this, two atoms hooked together, and when it warms up, when you give it energy, what can it do? Well, obviously it can move X, Y, and Z, but it can also begin to rotate. And if you look closely at this, if I hold this here and I call this a y-axis, it can rotate and have energy of a rotation around a y-axis. The axis coming out to you, call it the z-axis, it could rotate around that one too. And so I would call those 2 more degrees of freedom. Now this axis, which you might call the x-axis, I guess is a rotation, but we're back to the monoatomic gas here. There's not really a radius to it. I mean, it's not like the bond length. And even this isn't a good picture, because if this is an atom, which is 1 angstrom in size, where's most of the mass anyways? Yeah, in the nucleus, 100,000 times smaller than the atom itself. So when you rotate something around, when you rotate the atom around, it really doesn't rotate much. I mean, in terms of energy, it may have a large speed because it doesn't have much energy that's needed. But the amount of energy is very, very little. And so looking at a diatomic gas, I would say it translates X, Y, and Z. It rotates around 2 axes, but the third axis of rotation is just not that important. And so just like the rotations weren't important there, they're not that important in here. Yeah?
Maybe it's not applicable to this class, but is the center of mass where it's like a diatomic molecule in the center?
Yeah.
Even though like it has the bonds and stuff are holding it or not?
Oh yeah, remember
they're both the same atoms.
If they have the same mass, then the center mass will definitely be in the center. If it's something like carbon monoxide, it won't quite be in the center, but it's going to be, I mean, oxygen and carbon aren't that different in mass, so it's pretty close to it. So it'll be rotating around its center of mass, definitely. Well, here's what I'm getting at here, is when an object begins to get enough energy to rotate, that happens at about 100 degrees. And so when you look at the specific heat of a diatomic, less than 100 Kelvin, really this molecule never does begin to rotate. It only translates. So what do you expect for its specific heat? Yeah, kind of the same as you got for the monoatomic, where we did not include. And so when they measure the specific heat at low temperatures here, you can see that it's 3/2 R. When you start to get above 100 degrees, which we are above, and I shouldn't say degrees, 100 Kelvin. When you get above 100 Kelvin, then it begins to rotate around those two different axes. And so in this area where we live, somewhere around this 300, the specific heat, as we'll see, comes out to be 5/2 because you have those extra 2 degrees of freedom. And that's all we're going to worry about. You can also see what begins to happen again above about 1,000 Kelvin. You can see that it jumps up even higher as it begins to have other options of vibration. And in this case, it's vibration, and it lists the 2 where it can either expand back and forth or flap back and forth here. Okay, and so it puts 2 more degrees of freedom. So as we get to the more complicated molecules, you can see it gets a bit more complicated, but as some of you said, here's what we're going to say. How many degrees of freedom? Well, in the area of room temperature, we'll say there's 5. We'll say it can translate, and it can rotate around 2 axes. It's not warm enough to really do much of vibrations or anything else going on that, because the atoms do have electrons. So we will come back to here and say we have 5 degrees of freedom. But if you do exactly the same type of logic, you would say how much energy total is in a container of gas? You got 5 degrees of freedom. Each degree of freedom gets 1/2 kBT, and there are n of them. If you set the volume equal to a constant, so no change in volume, the work is 0, and so the change in internal energy is equal to the heat. The change in internal energy here would be 5/2 kBT times N, and that should equal to NCV delta T. If you hook those 2 together, you get your 5/2 NR, and I should have put this as a delta T, I guess. Delta T NKT, or delta T CV. Delta T's cancel off with an N, and CV should be 5/2 R. Yay! So, as hopefully is being shown in this little diagram, the specific heat is 5/2. And if we go back to that chart we were looking at before, you will see that the things like hydrogen, nitrogen, oxygen, even carbon dioxide. Ooh, this is a bad example. Yeah, chlorine has too many other things going on. So ignore this one. Chlorine really hooks to itself. It doesn't make a really good diatomic gas. And you can see that. It's kind of the oddball out. So not counting that, you can see that all of these come out somewhat close to the 20.8 that we calculate for the 5/2. A perfect no, but reasonably close to tell us that maybe there's a few other things going on, and of course there are, but in the simplest model we can say there's 5 degrees of freedom here, and that would be its specific heat. And then if you went on and did the same math here that we said, well, what if you hold the pressure constant? Then the work equals minus P delta V again. And so E equaling Q plus W means that Q is E minus a W. The E, as we just said, was the 5/2. Actually, I'll just write it as NCV delta T, and then minus a negative P delta V. Now let me pause again. Did you notice what I just did here? I went to calculate E, and I used CV. And yet, it is not a constant volume problem. It is a constant pressure problem. Is that okay? Yeah, it is okay for the E, but not for the Q. Right? In fact, for the Q, I would have to put NCP delta T, because the process we are talking about here is constant pressure, whereas this process is not really constant volume, but I'm going to use a constant volume because I have a state function. Yeah, right. Then, if I go ahead and did what I did over to here, write this as nR delta T, you can see I've done nothing different than I did before, and that is Cp comes out to be Cv plus an R. So none of this is going to change whether you have 3 degrees of freedom or 5 degrees of freedom or more degrees of freedom. You're always going to get Cp equaling Cv plus R. It's going to be one more, and you can kind of see that again. So if this was 5/2 R, we now add an R to it, and we get 7/2 R for Cp. Then sure enough, you take 7.5, you're going to be in this category of, in fact, maybe I will, what is 7.5, 7/2 times 8.31, 29.1. Pardon me?
Did you get that CP from that equation?
I got the Cp.
Yeah,
Yeah, so Cp is Cv plus an R. Cv is 5/2. And sure enough, what I say, 19.1. These all come out to be near 19.1. The difference between them is 1 R. Right? Warning, this can drive you crazy. Absolutely crazy. Cv is what? 3V is what? Okay, so again, Cv depends on what type of gas we're working with. And so don't miss that, right? Because it has to do with the number of the freedoms here. And so in this case it's 3/2, and in this case it's 5/2. Here's one thing worse. What was Cp for the monoatomic? 5/2. What was Cv for the diatomic? 5/2. One's a Cp, one's a Cv, one's a diatomic, one's a monoatomic. Keeping these straight can drive you batty. So keep it straight here. And I always just remember the number of degrees of freedom. I know I have 3 degrees of freedom for the monoatomic. Add an R to it. I got 5 degrees. Add an R to it. I have add an R to it. So we'll talk about that next, yeah. Well, all of these are in that range of, is that what you mean, from about 100 Kelvin to 1,000 Kelvin? Yeah. Is that what you meant? Yeah, yeah. So in that range. Yeah, yeah. So, which is most of what we do. In fact, I can't even think of a problem where we're going to be outside of that range. Clearly, the whole world is more complicated than that. And so if you were really designing a electrical grid and power supply, and you want to ask yourself, are we going above 1,000? Yeah.
So if you're working with the absolute temperature, like Q equals nRT,
Yeah.
and you're doing a conversion or something, should you just assume that these stay the same throughout the whole way up to the temperature?
I guess I'll say yes to that, but I'm not sure it ever becomes a relevant question, because you're often interested in how much energy do I add or how much do I take away. So I can't think of a problem where we're going to warm the gas from absolute 0 up to 300. Does that make sense? If I did, then I would have to do the different levels, right? Right. And so I would guess I would call that a more complete model, and a model that I don't think we're gonna touch on. Like we do in mechanics a lot. We say, don't worry about the air resistance, right? Or solid to solid friction, the kinetic friction, treat it as a constant. Yeah, right. Really, is it? Well, no, but it's a good place to start. Right? And so same thing here. Over a big range, it's pretty reasonable. If I continue on here, maybe I should put gamma up here. Remember, gamma is then Cp divided by Cv. I haven't really explained why we want gamma yet. That's, like I said, kind of the last step here. But as I put this in, this would be a 7/2 R over a 5/2 R. The R and the halves cancel, and you end up with 7 over 5. That's 1 2/5, so that's 1.4. And sure enough, other than the chlorine, we're right in that range of 1.4, and chlorine's reasonably close. And so there's our ratio. And then the last gas, kind of where I was hoping to get last lecture here, is what if I had something more complicated? Something maybe that looks like this. And it kind of looks like natural gas here, methane. How many degrees of freedom does it have? Now, fortunately, if we keep this below about 1,000 Kelvin, we don't have to worry about all these different vibrations that can take place. Okay? So, the polyatomic will just say, again, it can move X, Y, and Z, and it can rotate. That would be the y-axis. That would be a z-axis. But added to this is we would have energy associated with an x-axis rotation, because now it has a three-dimensional structure to it, unlike this diatomic, which is kind of linear in nature here. And that's the only thing that would add, except when we get to the fact that, well, it could do a little shaking this way. And so, as you're going to see, our model becomes less perfect as we get more and more complicated things, more and more degrees of freedom, more places the energy can go. But eliminating all those other places, I would say I have 6 degrees of freedom. And so as I go through this, I would have E equals 6 1/2 kBT times the number of molecules. And after doing the same work, what would I get for CV? Yeah, 6/2 R. 6/2 R. And if you want to call it 3R, that's fine, but I prefer the 6/2 R because it fits in with the pattern. How many degrees of freedom did I have here? 3. How many degrees of freedom did I have here? 5. How many degrees of freedom do I have here? 6. And it allows me to think about what is CV. And then once I know what CV is, I can always add an R to it to get CP. So in this case, CP would be the 3R plus the R, which is 4R. Again, I prefer to think of it as 8/2 R, so that it follows the pattern of the 1/2 degree of freedom there. But if I then get my calculator out and go 3 times 8.31, I get roughly 25. And so sure enough, looking at some of these other ones, 25, well, carbon dioxide is probably a poor one to think about because that's a nice linear molecule again. I know it's got 3 atoms to it, but it's also linear. And it doesn't really give me a 25, although none of these really give me a 25 exactly. So as you can see, it does have its imperfections. If I add an 8 to it, I get, roughly those. So they have a difference roughly of there. The gamma then would be this ratio of CP to CV. And so that would be 4R over 3R, which would be 1.33. And again, somewhat in that ballpark. So you can begin to see that the polyatomic kind of works. It's obviously something more complicated is going on. In fact, I'm not sure we really even do any problems with the polyatomic. Because of that, it's kind of getting too far away from our model. Most of the things we do is diatomic. It makes sense. I mean, that's what we have in front of us. We have a bunch of nitrogen, and you'll see in the next chapter that's what we're going to do is we're going to put a bunch of oxygen and nitrogen in a chamber and with a little bit of gas molecules and ignite them. Boom! And those nitrogen molecules are going to go flying around, bouncing around, and what we're really going to care a lot about is what's happening right here. these two, these diatomic molecules, as they bounce around and push our piston and make our car go and turn our turbine to give us electricity. Yeah.
So what's gamma useful for?
Well, I'm glad you asked. I really haven't explained why I've been looking at the ratio. And so the last step here in the chapter, or at least the last step I'll cover, your author has a section on the distribution of speeds in there. And I decided I'm going to kind of just brush over that. We kind of talked a little bit about it. So take a read on it, but I'm not going to test you on that little formula. It's a statistical section that's really kind of nice, but at the same time, the author just starts off and says, oh, well, this math is beyond you. It's statistical, calculus, statistics with calculus, and you'll see it next time, and here's the results. And so maybe I'll show you the graph here about as far as I'll go with that. But the gamma one that you're asking about is what I care about, is because of this. If I take a gas with a PV diagram, in a PV diagram, what would an isovolumetric process look like? We've done that one, right? That's probably the easiest one. What would it look like? A vertical line, right? You would have a line that you would move upward if you were going to higher pressures, so you were, say, warming the gas, or you would be moving downward if you said you were cooling the gas. And that one's an easy one to understand. It's a straight line. I bet you know the equation of a vertical line, right? It's just V equals a constant. No problems there. The other easy one we did is isobaric. What would isobaric look like? A nice horizontal line here. So maybe I'll just put a line there, and maybe I'll put an arrowhead both directions, depending if we're going to lower volumes or higher volumes. So here we're squeezing the gas, and obviously if we're squeezing the gas but the pressure isn't going up, we must be cooling it. And likewise this way, if we're expanding the gas without the pressure going up or down, we must be warming the gas here. And so again, nice flat line. I think you know the equation for a line. The isobaric one's pretty easy, all right? Just P equals a constant. How about the isothermic? We did talk about that one. That one's a little bit harder. Okay, and so the isothermal one, and maybe it's best if I grab it off of the chart here from your textbook, your author shows these isotherms. And in this PV diagram, this would be all the points that are at the same pressure. It's an isotherm. What shape mathematically does it have? This is the hyperbola, right? This is, using the ideal gas law, PV equals to nRT. But since we're keeping the temperature a constant, then what you really have is pressure times volume equals a constant. Now, of course, that constant depends on how many molecules you have and what temperature it is. And it should look just like you learned in your math class, x times y equals a constant, or y equals to some constant over x, right? And so that's that plot. So that one's, I think, a little harder mathematically, but not unreasonably hard. That's why we already talked about it. But did you recall? We have not given you the equation for the adiabatic line. We were waiting until we got the gamma function. Okay? Because there is an equation for this. And let's look again at the adiabatic process. I think your author's done a good job here of saying, let's look at two isotherms. If this is T1 or T initial and this is T final, depending on what direction you're going, okay? This is the equation for two hyperbolas, two different temperatures, right? If you have a gas and you compress it adiabatically, if it is, say, here, and as you compress it, so maybe I will start here at some initial volume. If I squeeze it to some final volume, comparing these two, if I were to squeeze it at constant temperature, what would happen? Well, at constant temperature, I guess it would go up to there, right? And so we would have a final pressure. The pressure has gone up. But if you do it adiabatically, does the temperature remain the same?
No.
No, and why not?
Because it's the function of E equals Q plus work, but since Q is 0 because there's no heat entering or leaving the system, you will have all that's going into
Okay.
energy.
Okay. Stepping out of the math for a moment, I just hit the molecules, right? I make them go faster. I'm doing work on them. And once I make those molecules go faster, that is an increase in the temperature. And so compressing a gas quickly, see, I'll put it right about there, that makes the temperature go up. If I did it slowly, the temperature would have tried to go up, but because I'm doing it slowly, this, as it's trying to warm up, would then cool down because it's sitting in the room. And so a slow compression might be a constant temperature compression, whereas a quick compression would be an adiabatic one. But the point is the temperature would go up, and what would happen is it would look more like that red line on there, or brown line. I'll put it as red, and it would go like that. And so the final pressure would be a little bit higher with an adiabatic compression instead of an isothermic compression. And hopefully that makes sense, because the pressure during the adiabatic should go up for two reasons. Number one, you have less volume, but number two, more temperature. And so I would expect the pressure to be a little bit higher than this. So both compressions, whether isothermic or adiabatic, I do expect the pressure to go up. And it does. But I expect the pressure to go even higher during the adiabatic, because not only do I reduce the volume, but I make the molecules go faster. And so there is an increase in the temperature. I go over to the next isotherm, if you will. And that's what your author is trying to show here. Yeah.
I notice you have the red arrow pointing up. Does that work? They have it pointing down. Does it go either way?
Oh, yeah, now, of course, I think, yeah, good point. I'm mentally thinking about compressing it. What do they have here? Here they have an expansion. So they're going from initial to final. So just like the other processes, I guess I should put an arrow both directions. And I guess I didn't put an arrow both directions here. But we could go from a compression to an expansion. And in the expansion, if I start here and I compare the isotherm to the adiabatic, the isotherm would bring me down to here, whereas the adiabatic, the gas would be cooling, and so the pressure would end up a little bit lower than the isothermic process. As to be expected, the pressure should go down in both cases because the volume is getting bigger, but the pressure should go down even more in the adiabatic because not only did the volume get bigger, but also the temperature got less. And so a bigger drop in pressure as we expand, or a bigger increase in pressure as we compress during the adiabatic, during the isotherm.
So for the isothermic, we have to put Q in to keep it at that same temperature, but in the adiabatic, you're not doing Q0.
Right. Now you say put it in, that would be during the expansion.
Okay, yeah.
Right? So if I were to come over to here and I wanted to expand this gas in an isotherm, I would pull up on it. And at first you would say, okay, that's kind of cooling the gas, but because this is sitting in the room, this would start to warm. So heat is flowing in as I am pulling this up. If I don't let heat flow in, either by wrapping it in an insulator, that's one way to say it's adiabatic, or the best adiabatic is just do it quick. Whoop. Didn't have enough time for heat to flow in. But both of those the heat can't flow in, and so that's an adiabatic process. Did I see another question? All right, now you can see where I'm headed with this, I hope.
So adiabatic just simply is a quick change in pressure.
So one way of getting adiabatic is very quick change, yes.
In pressure, or just in pressure, or strictly for pressure, or volume as well?
Well, you change in volume, but that change in volume would also have to correspond to a change in pressure, which would also have to correspond to a change in temperature. And that's what I'm after here. We have not given you the equation for this red line. Right? Don't we know the equation for constant volume? Don't we know the equation for constant pressure? Don't we know the equation for constant temperature? But do we know the equation for the adiabatic? No. But we can figure it out now. We have enough tools. We needed to do CP and CV, and you're going to see that that's going to come into play here in just a second. And with between that and a little calculus, we'll get a nice mathematical shape of that curve. And so we'll have the equation for all four of our curves. Yeah.
Shockwave from an explosion, would that be constant pressure and volume as it goes out?
No. I mean as the shock wave goes out, and it say there's molecules here, and the shock wave hits it. What the shock wave really is a compression wave, and so what it would do is it would take those molecules and compress them, and it would do it very quickly. And so I would call this an adiabatic process. And so as it gets right here, it compresses them. And that, of course, makes a high pressure zone. That's what's going to say this shock wave where it's high pressure. If this hits the building, that's what knocks over the building. But it's also very hot, extremely hot, because we have just compressed the gas and got up to a very high temperature. And and the building can light on fire. I mean, the explosion is over here, but 100 feet away, or if this is an atomic blast, miles away, when that shock wave gets to that building, it hits it and it's on fire. And not just knocks it down, but it ignites it on fire. Because again, like that fire plunger you saw me, I mean, so I would call the shock wave an adiabatic process.
The shockwave is actually causes the fire, not coming out.
Well, I would say it's one way. I mean, there's many ways of a fire starting. I mean, if this is a building and you knock it over, all the gas lines are going to leak now. And then, and now there's going to be all kinds of fires because of the gas lines and the stuff that's in the place. Yeah.
So yeah, I just was wondering that because I was reading something on like an Armageddon size like comet or whatever it is, and part of it was that like the size of that would also set an entire continent on fire, and at first I was like, what? How? Like?
Oh yeah.
And I was like, the flash from the heat, but is it from the shockwave itself?
Yeah, the shockwave itself would just, as it flies over, it's like California here, as that shockwave hits down, it's just going to light every house on fire. Probably knock them down first, so you don't have to worry about that fire part. They're wiped out first, then they catch on fire.
Don't worry.
Yeah. So, yes, and your body will vaporize before that. So don't worry about all that.
I'm also thinking about that.
And I might as well mention it. I mean, you said, there's other way to catch on fire. If this is an atomic blast, the intense radiation coming from it can be enough to light the object on fire. And that actually travels faster than the shock wave. So atomic blasts can be interesting because you have this blast, and the building actually then catches on fire, then gets blown over. Because the solar energy, the light energy, and other particles hit there first, lighting it on fire before the shock wave can get there, depending on how far it is away too. And I know we got off topic, but I mean, this heating effect is, if you're into the science of weaponry, it's really neat. They call this a Mach Y because if you take a ground and you blast the bomb in the air, not ground level, you think, why blow it up into the air? But here's why. Because as the shock wave travels out, you're going to get a ricochet off the ground combining with that wave, And what will end up happening is a superpositioning of the two waves. The shock wave is twice as strong as it would have been had the blast been at ground level. So you blow it up in the sky. That's why, the atomic bomb over here, Hiroshima, was, thousands of feet in the air. You bounce it off the ground. And more than that, because of the warming on the ground, here, that warming effect changes what would have looked like a superpositioning of this to look more like a superpositioning of a solid wall. And because this will travel faster than that. And so it looks more like what they call a Y. So it's a shock Y. And the added effect of this can be amazing compared to without the adiabatic warming here. And so, yeah, this shock wave. And, of course, how big the shock wave is really depends on how solid the ground is. And you see that really well when you look at the data of what happened in Hiroshima versus Nagasaki. Nagasaki has a soft ground. And it lost a lot less damage after the Nagasaki explosion versus the Hiroshima one. Because this reflection and the adiabatic warming and the shock wave wasn't nearly as intense.
Does nuclear need to be stronger than that? It's already strong enough or as is.
Is what?
Does the nuke really need to be that strong? It's already strong enough as is.
I guess depends what's your target? I mean, if you're trying to blow up Los Angeles, it's not big enough. No, Los Angeles is a big place, right? So I mean, this is only going to wipe out 10-mile radius, right? I mean, that's just LA to Hollywood, You still have Long Beach and stock here, right? I mean, come on. I'm sure North Korea is thinking about this daily. Oh, I should go down that road. All right. All right, well, anyway, so however I got on this, but I guess it was a shock wave. Shock wave would be adiabatic. And you can treat sound waves the same thing. If you remember, we kind of touched on this. We just didn't have enough time, but we did in the sound waves. We did the bulk modulus. We said that the speed of sound would be related to that bulk modulus way back in chapter 18. And we didn't have time, and still don't have time to do it justice. But that would be, the bulk modulus is related to CP and CV because the sound waves, as they go through, are an adiabatic compression, and their speed of them then can be calculated from thermodynamics. And that's where that equation came from back when we did sound waves. It was calculated through our thermodynamics. No, not that we've done it and not that we will do it, but your next class probably will. So when you transfer to UCSB or Poly or wherever you transfer to, I'm sure in your thermodynamics class you will end up calculating what is the speed of sound and the whole bulk modulus thing. All right, well, as I said, I was going to try and show you the whole equation here, and so let's take a moment to say, what is the equation for the adiabatic process? What is the equation of this red line? And you can see it here when you put the ideal gas law, PV equals nRT, together with the first law of thermodynamics. I'll start here with the ideal gas law, and I will take the derivative. I'll just take it with respect to temperature. I guess it doesn't matter. We're going to do a differential anyways. So this would look something like P dV dt, then V dP dt. Right, and so it's a product rule. It's both pressure and volume can change because the adiabatic one is the hardest one. All three things change: pressure, volume, and temperature, and that would have to equal to nR. Or moving the dt to this side so it looks like a differential form. Here's what you're saying: when a gas changes, pressure times its small change in volume, volume times its small change in pressure must equal the number of molecules times the gas constant, times a small change in temperature. And so that's how changes in pressure, volume, and temperature are all mathematically related. And of course, it's easier when one of those doesn't change. But when all three of them are changes, that's the best we have to work with. If we look at the adiabatic process, what was important here in the adiabatic process? What does this big word mean? Yeah, Q equals to 0. So E equals just W. And W, we said, at least on a small scale, so I'll say dE equals to dW. On a small scale, isn't that P dV? And now I'm going to invoke what we did already here. How can I calculate dE? Wouldn't that be NCV dt? Now, maybe I should emphasize. Notice I just calculated a small change in the energy. What did I use to calculate a small change in energy? Constant volume. Can I do that? Yes. Is this a constant volume problem? No. So, why can I do that? It's a state function here, right? And so I can use the CV for any case, as long as I'm substituting it for E, not for Q. Q does not equal NCV delta T. That's what it would if this was a constant volume problem, but this is not a constant volume problem. That's why the Q equals a 0. But the E still works the same. Now, the reason I care about that is that I can do a substitution. I can get rid of the dt, or I can get rid of the dv, and then I just have two variables. Separation of variables and integrate. Yay, got equation. And so that's what I'm after. I've got three variables. Now, if I can get rid of one of those, I can do a separation of variables and integrate them. And so why don't we get rid of the dt? That's kind of the pattern your author took. Yeah.
How does deriving PV equal nRT make P times dV dt plus V dP dt equals?
Yeah.
All the way, like how does deriving P equal nRT produce that one? Yeah. How does deriving P equal nRT make that?
Well, I'm going to take a derivative of two functions. Product rule.
Oh, product rule.
Yeah. All right, so now you see the picture now. Unfortunately, I still got a lot of math to do, but here's the process, right? Ideal gas law. First law of thermodynamics. Applied to the adiabatic process. Remembering it's a state function. Put the dt into here and two variables, P and V. Separate, integrate, got equation. Okay, so we'll give it a try here. And so if I put these two together, I get P dV plus V dP equals to NR. The T becomes a negative P over NCV dV. Now you're beginning to see I've got dVs with dVs and dPs. So now let's do separation of variables. Let's get all the P's together, all the V's together, and integrate. Yeah.
You should get the negative PdV.
Here? Oh, this, I guess, is our definition of work. Work, which is the integral of force times distance, becomes the same as pressure, negative, times volume. And so a little bit of work would be a pressure times a little change in volume. Yeah. So there's the work and there's the dE. Okay, now if I divide everything by the product, PV, this will make a dV over a V with no P's in it. Yay. This will make a dP over AP with no V's in it. Yay. This will make a, is there a V somewhere? Yeah. Negative, thank you. There is a dV with a V in it. Right? This, believe it or not, is where the gamma is going to come in. Doesn't look like it, but you see the CV already. If I write this R as CP minus CV over CV. I can get rid of the R and have it written in terms of the CPs and the CVs. And so then the CV goes into CP, that's the gamma right there. That's the minus gamma plus 1 dV over V. Okay. And now, if you look closely at this, there is a dVV on this side of the equation and a 1 dV over V on this side of the equation. Now it just got easy, right? So this becomes dP over P minus gamma dV over V. Now, when I integrate both sides, this becomes the natural log of P. This becomes a minus gamma times the natural log of V, and then you might say plus a constant of integration. Yet to be discussed. But when you then move, well, I'll just raise it to a power first. So raise it to a power of E, raise it to a power of E. This just becomes pressure. This one, you kind of need to watch here. I'm going to move the negative gamma up there. So this is E to the natural log of V to the negative gamma times E to the constant one. But what's nice about this is the natural log and the E undo each other, and so this is V to the negative gamma times some other constant. Move this to the other side of the equation. Move it upstairs, and we actually have what we're looking for here in the relationship between pressure and volume. And this then describes that red line. That red line is described by a function that kind of looks like the isotherm. The isotherm was pressure times volume raised to a power of 1 equals a constant. The adiabatic now becomes pressure times volume raised to a power greater than 1 becomes a constant. And so that's why it's got more curve to it, because gamma is greater than 1. CP is always greater than CV. And so that's the equation we were looking for. Obviously a little more complicated to derive and a little more harder than I think to see, but obviously very important before we finish our 4 chapters on thermodynamics. This R, earlier on we said CP is CV plus R. Okay, so I'm going to replace the R with CP minus CV.
How'd you integrate the left side again?
Integrate left side here.
Yeah.
Okay, so then this term right here is the same as this term. So I cancel them off. Cancel, cancel. And so I have just a PdV. And I no longer have a negative gamma plus 1. The plus 1 canceled with that on the other side of the equation. And I just have a negative gamma. So what looked like was going to have a lot of terms all went away. Oh, isn't that beautiful? Say yes, yes, yes. What could be more exciting? Okay, yeah. Why Q equal to 0? Well, my definition is, what process do I want? Adiabatic. So once I do this step right here, everything beyond is only valid for adiabatics. And so obviously this result only applies to adiabatics. So that's that particular case I gotta focus on. Just adiabatics. All right, well, timing came out right. That leaves me about an hour here, and I've got 3 solid examples I really want to do, and 5 if we have enough time to say, hey, let's look at these, particularly all these processes, especially now that we got a mathematical form for the adiabatic process. We haven't had that before. We kind of introduced you to the adiabatic process earlier on. And I've always wondered which is best, and I kind of like the way the author does this. He doesn't give all of the information for the adiabatic, and that used to bother me, but over the years I've kind of discovered it's kind of good for the students to just get familiar with the adiabatic. It's the harder of the four, I think, and just kind of let them think about it conceptually in the last chapter before we throw all this math at them in this chapter, I think is a good idea here. And so hopefully that helps there. And so if I open up my notebook here, and I guess I should check. Did I cover what I want to cover here today? All right, so we did. Yeah. Okay. Let's me turn, and then to somewhere in my notes where I listed a bunch of problems to do. And jump on number 23. And so 23. Oh, sorry. Chapter 21. Problem number 23 says the following here. It says, maybe I'll just start by putting the number here on the board. Number 23 says a 4-liter sample of diatomic ideal gas is confined to a cylinder and is carried through a closed cycle. Now, let me stop there. Closed cycle. What do they mean by that? Okay, mathematically, delta E is 0. And in that PV diagram, what does that mean? Yeah, whatever happens, you end up back where you started. Which means we would end up with the same pressure, the same volume, and the same temperature. And since E is related to temperature, the total delta E of that process, as you said, would be 0. And that's going to come into play here. So that word, closed cycle, has a lot of implications. All right, but let's listen to it here. It says the gas is initially at 1 liter and 300 Kelvin. First, its pressure is then tripled at a constant volume. Then the gas is expanded adiabatically to its original pressure. And then finally, the gas is compressed isobarically back to its original volume. All right, so there's the closed cycle. And my suggestion for you, and the big reason I picked this problem, and well, many reasons, but draw the PV diagram. As I said in our mechanics, our free body diagrams were very powerful tools. We talked about those, and so just like we use those in our mechanics, draw your PV diagram. It will help you with the thought process. So, here's what they said. They said we are starting somewhere, and they say it's 300 K. So that's probably around room temperature. All right, so 300 K. They also say it has a pressure of 1 atmosphere and a 4 liters of volume. So if I come down here and put 4L for 4 liters, if I come over here and put 1 ATM, this is the position where this gas starts at. Its pressure, its volume, and its temperature, all kind of listed in that diagram. PV, and once P and V are decided, temperature is decided at least based on the number of moles. Okay? Because it says that the pressure is tripled at constant volume. So what would that look like here? Well, it's tripled. Second, third. So we would go up to 3 times the pressure. If we started at 1, 3 times that is now at 3 atmosphere pressures. Since it said go up at constant volume, it's a vertical line. That's our isobolometric path, right? All right. So first, its pressure is tripled under a constant volume. Then is it expanded adiabatically. All right. So that's what's new here. That kind of that brown line. That's what it would look like. It's expanded adiabatically until we reach its original pressure. So the original pressure is somewhere along here. So an adiabatic expansion would look something like that. Okay? And I know on a graph it's kind of hard to tell whether I'm drawing an adiabatic or whether I'm drawing an isotherm, but that is adiabatic, okay? I probably should make it steeper. That looks more like an isotherm.
That was it. I was going to say, whenever you have adiabatic, it's always going to be less change in volume than change in pressure.
No, because that depends. No, because depends on the number of moles and where I am on this graph. See, if you can, in this picture, they have it where it's curved high, and it looks like it's a drop in pressure more than volume. But what if I was over here? Then it would be like this. So it's not quite that simple, but I don't like this picture either. So I'm going to fix it. How about that? But just to make it real clear, I'm going to put Q equals to 0 there. Okay, that's an adiabatic process. Okay, and make it kind of clear what direction I'm headed. I'm doing an expansion here. Okay, a little more ink in it. All right, and then the third process, I forget what they said, was this isobaric. Finally, the gas is then compressed, so smaller volumes, isobarically back to its original volume. So there's how we get back to its original volume. It goes like that. All right, so there's my closed cycle. Okay, 3 processes. Isovolumetric, adiabatic, isobaric. Okay?
Tell you the specific order it's at, or can you just...
And they told me the order that it went. Right. I mean, because it could have been very different, right? If it was here and they compressed it adiabatically, it would have gone like this. And then if they expanded it isobarically, then it would have went like this. And then if they reduced the pressure isovolumetrically, they would do that. And so I'd have a different path. A different path, a different shape, a different area, different heats, different Qs, right? All those things would be different. And so I need to know the path that it takes. And that's why the picture really helps. Okay, and I know it has to be closed. All right. I also know, by the way, it's diatomic. They said that at the beginning. Keep that in mind, because does diatomic matter anywhere here? Because it's adiabatic, right? An adiabatic has a gamma in it. And doesn't gamma depend on CP and CV? Yeah. And so I think that the fact that it's adiabatic is going to come into play here. Real important here. But here's the question now. The first question says, draw the PV diagram. All right, already did that. I wish they wouldn't even have asked it, because I just want to emphasize. You would do that anyways, right? Not even asked. You're going to do that. Very helpful tool. End of story. All right, B. B says, determine the volume of the gas at the end of the adiabatic expansion. Okay, so they're after this part of the question. Where is the volume? Well, let me kind of give you the whole chart here. Again, the reason I picked this one is I started to do this in the last chapter, is I think it's very helpful to do this. Maybe label your positions as A, B, C, right? And then when you make a chart, you could say at A, at B, at C, what is the pressure? What is the volume? What is the temperature? In some problems we have enough information to answer all these. Other ones we don't. I don't know if this one does or does not. But that would be my 3 states. I would also include, look at the process from A to B. Look at the process from B to C. And then look at the process from C back to A. Looking at those 3 processes, I could look at the change in internal energy. I could look at the heat added. I can look at the work done by the gas. And so I've got one chart discussing what happens in terms of the energy. I got another one, what we would call the state functions. What is the state of the gas? What is the pressure, the volume, and the temperature here? Okay. And so a lot of these I already know. For example, at the very beginning step here, I know that the pressure is 1 atmospheres. I know the volume is 4 liters. I know the temperature is 300, and maybe I should just put my units up in the top of the chart so I don't have to keep writing them in the chart. How's that? And I think the charts help because what does that tell me right away? What do you think? I know PV and T. I can find N, right? I know how many molecules I have. I don't know if I'm going to need that or not, probably, if I'm going to be calculating energies, because the energies have to do with how many molecules I have. And so I have a good suspicion that that little line there is a big hint to me. Well, I'll keep going because when they went to B, they told me the pressure went up 3 times. They told me it was isovolumetric, so what does that tell me? Volume's still the same, right? And again, if I know any 2 of these, I can find the third as long as I also know the number of molecules, which I do, but back here, right? All right. I don't know if I'm going to need it, but that's the information they gave me. A C is probably the hardest one at all. They said it expands down to its original pressure. Okay, there it is. But I don't know the volume, and that's really the first question they're asking right here. Right? What is that volume? And of course, and I could also find the temperature. I don't know if they're going to ask that later. Okay. And actually, that's enough in my chart to give this away to me, because how are B and C connected? What process? Adiabatic. Do I know the equation for an adiabatic process? Oh yeah, that's why we just went through all this math, right? So I know that the pressure at B times the volume at B raised to a power of gamma equals some number, a constant. But anywhere along that adiabatic process, which would also be point C, would equal that same constant. Now you can choose to find the constant if you want, because we do know B is a volume and a pressure already. However, I'm just going to avoid finding the constant and set the 2 equal to each other and say, all right, pressure at B times volume at B raised to a power of gamma must equal the pressure at C times the volume at C raised to a power of gamma. And I know 3 of these 4, don't I? And I know gamma because it's diatomic. And so as I fill these in, I will go, okay, what's the pressure at B? Well, 3 atmospheres. What's the volume at B? 4 liters. Raised to a power of? All right, well, why don't we start with CV? And again, another important reason. This is how I remember it if it helps you. How do I remember CV? It's diatomic. How many degrees of freedom do I have? 5. So CV must be 5/2 R. What would CP then be equal to? 7/2 R. Gamma would be the ratio between them, right? 7/5, 1.4. All right, so 1.4. So I don't in any way try to memorize gamma or CP. It's just CV. I know CV for each of these. It's the number of degrees of freedom. That's why I said the number of degrees of freedom will become a powerful tool for you. And you're just beginning to see the tip of the iceberg. And then, unfortunately, we're going to leave our thermodynamics right when we get to some really hard stuff. And so we'll have to wait till next year. So, bummer. Maybe UCSB will let me teach it over there someday. You know, just kidding. I don't have time. But that would be a fun class to teach. All right. But there is the first line. Going over to the other line then, I will do a pressure at C, which would be 1. And then I would look for the volume, which again raised to a factor of 1.4. So, got a little bit of math to do, obviously. CV would then be written, and I'll just write it out because this is how I like to do it on my calculator. Saves me a little time. It might save you a little time too. Is I take the 3, I multiply it by the 4 raised to a factor of 1.4. Then, how do I get rid of this? Yeah, I raise it to 1 over 1.4, right? Because 1.4 raised to a power of 1 over 1.4 leaves volume to a power of 1, right? All right, so getting out my calculator, and we could even do the distributive property before then, or distribute the exponents, I guess I should say. But I don't even need it. I don't even care for that. I just go straight for the calculation and go, this is a 3 times a 4 raised to a power of 1.4 and hit enter. So that's inside here. Now I need to raise it. So I hit the caret for raise. And I just do 1.4 and then hit reciprocal key. 1.4 reciprocal key and then hit enter. And so assuming I have done my math right, I get 8.8. Question? Okay. If you like 7/5, I don't, good. Sure. Sure. But I guess I was getting at is take advantage of that caret key and the reciprocal key. I mean, just put the 1.4 reciprocal, and it's really a powerful. I guess that's why I prefer the 83 and the 84. Is it the 86 or the 89s? They kind of bury that reciprocal key, and you got to do a shift 2 to get to the thing. And I like the reciprocal key on top. It's good for our optics. It's good for our electronics. It's good for our thermodynamics. 1.8. Anyway, so I guess I've answered this question. That's a 1.8 or 8.8. So I probably should have drawn it just a hair more over there to be to scale there. Okay, but there is the start of my chart here, which says determine the volume of the gas at the end of the adiabatic process. C. Find the temperature of the gas at the start of the adiabatic process. Okay, so they're after the temperature at B, aren't they? What is this temperature? All right, well, again, now that we've done the adiabatic, can I clear this part here? Or I don't think we'll need this for a while, if at all, so maybe I'll leave that there and turn that off here. But again, you want to stop and think about the B is, of course, connected to the C with an adiabatic. So you can connect the B and the C if you want. But for that matter, the A and B are connected with an isovolumetric. I think that might be a little bit easier. Okay, and so this is the puzzle you have to do. And I think laying out this grid helps with that puzzle. And I think I'll connect the A and the B, because the A and the B have the same volume. And so I know that for an ideal gas, initial pressure, so pressure at A times the volume at A divided by the number of molecules times the temperature at A equals R. That would have to be the same as the pressure at B, the volume at B, divided by the number of molecules divided by the temperature at B. And I want to know the temperature at B. And so looking at this, the number of molecules cancels off. So I don't even have to calculate that. The volume of A and B are the same. I even know their numbers is 4, but I'll just cancel them off. And so what I get is the pressure at A divided by the temperature at A must equal to the pressure at B divided by the temperature at B. And so that's the connection between A and B in this example, in this process. And so put those numbers in. Do I know the pressure at A? Well, that's a 1. Do I know the temperature at A? Yeah, 300. Do I know the pressure at B? 3. Do I know the temperature at B? Well, no, but I'm going to find it. So the temperature at B must be 900 Kelvin. 3 times 300. So there is the 900. And so I've answered their next question. What is the temperature? Determine the, find the temperature. B, find the temperature at the end of the cycle? Do they really say that? Did I skip something? C, find the temperature of the gas at the start of the adiabatic. Oh, that's what I just did. D, find the temperature at the end of the cycle. No, I think they meant the whole cycle. Yeah, it's kind of a, well, maybe that's why it's a good question. It's a very easy question if you see it. If you don't see it, you need to see it. What is the temperature at the end of the cycle? 300. It gets back where it started to. And so when you get back here with that given pressure and volume, the same number of molecules, PV equals nRT, you better get back to the same temperature. And so, it doesn't really fit in this chart because there it is. We get back to A, it's 300. So the answer there is 300. Ooh, what was the net work done on the gas for this cycle? The net work done on the cycle. Now, I'm not sure if I'm going to need it, but I'll tell you what. Why don't we complete this chart and answer this one before we go to the energy chart? Okay? And so, what's this one? Well, again, we know that B and C are connected through the adiabatic, but we also know A and C are connected isobaric, right? And so maybe that's the approach to go. The pressure at C, the volume at C over the number of molecules and temperature at C would be the same as the pressure at A, the volume at A over N times the temperature at A. And what's nice about that, of course, is A and C are connected with the same number of molecules. That goes away. But are also, this C to A is the isobaric, so they have the same pressure. So the pressure at C and the pressure at A go away. And so the volume at C over the temperature at C, that's what I want to find, is equal to the volume at A over the temperature at A. And so the volume at A was 4, was it not? 4A. And the temperature at A is the 300. The volume at C is what we just got done doing. And so that is 8.8. And then I've got the temperature at C. So I'm going to have to get my calculator here. But I can also get that temperature at C. I guess it would be 8.8 and cross multiply gives me a times 300. That then divided by 4 gives me 660. And so the temperature at the end of the adiabatic process, which again they didn't really ask for, but I may need it, is 660. And doesn't that make sense? Because it was here at 900, it expanded adiabatically and it's going to lose some temperature. Now, it should not go all the way down to 300 because I then have to cool it to get back to the 300. So this number here better be less than 900 and more than 300. And sure enough, it is. Bunch of questions, yeah.
Would it be possible to use P sub B and B sub B to find B sub C? Like you don't have to use B sub A, right?
Right.
Okay.
All right. Right. And let me emphasize this. This is a puzzle. And like a puzzle, you know, people will choose to approach this different ways, whatever you see. And so if you do a jigsaw puzzle and you lay it out, some people start doing the corners and the edges first. Other people, they look at the landscape and, you know, maybe it's this lake with snow-covered mountains, and they start laying out and they see all these white pieces going. The only white in the picture is the snow on the top of the mountain, and all of a sudden as they're turning pieces over, they've put together the mountain already because they've put together the white pieces. So, you know, your approach, there's not just one way to do a puzzle. We all will get the same puzzle completed when it's all done. Just a matter of what we do first and what direction we go from there.
So across like A, PV equals nRT holds.
PV equals nRT is always true for any of the gas anywhere. So, and that's kind of the connection. You hit on something I want to make sure everybody sees. Take advantage of PV equals nRT. If you feel like you're stuck, just go. Let's look at PV equals nRT. That's probably a good place to get unstuck because it's all connected. It's always PV equals nRT. Mm-hmm. Yeah, for any gas. Yeah.
Like in one system, like the number of moles cannot change.
Well, right. In this case, our number of moles doesn't change. And I don't think we ever do one where it changes. Again, it's an introduction to thermodynamics, so we don't change the number of moles. And plus, to change the number of moles, that's a chemical reaction. And again, this isn't a chemistry class. So for both those reasons, I don't think we ever really change the number of moles. Yeah. Yeah. Even when we burn gasoline in the next chapter, we're going to say we don't change the number of moles. There is a chemical reaction taking place in there, but when we burn gasoline, most of the atoms in the container are the nitrogen, not the gasoline and the oxygen. So all we do is warm the nitrogen, really. So we're still going to take that approach, yeah. Yeah. Okay, so I've got the temperature, and it does seem to match. That's a good sign. And now maybe I can go on to E. What is the net work done on the gas? So maybe back here in the chart, I should put total underneath here and start filling these in. And again, I don't know if I have to fill in every single last piece in order to answer this question. But maybe I should fill in every last piece so that you will feel more comfortable on the homework as you start doing these problems here. I will start with what I hope is the easiest one on this chart. What's this?
0.
Yeah. So the total better come out to be 0 for the total change of internal energy. And keeping in mind the first law of thermodynamics, if you know any two on here, you also know the third. So I am halfway done in finishing this row. Right? Here's my suggestion. Start with the state functions. Again, it's a puzzle, so that's not true for every case. But what was really nice about that state function? This is what I wanted you to see. Yeah. Yep. Yep. I don't care what gas you have. Delta E is NCV delta T. Right? That is really powerful. And if you've already done this chart right here where you have the temperatures, you can get the energy just in a piece of cake like that. Even though, again, this process may not be isovolumetric. Use the equation for constant volume. It works because it's a state function. So all we have to do is know how to derive it in one case, and it's true for all cases. Too bad the Q's and W's don't work that way, so they're going to be a little bit harder, but that's why I say focus on the E, the internal energy first.
I know you said we wouldn't, but changing the temperature, does that equation change or does CV change?
CV changes. Yeah. 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 All right, so using that information, I can actually calculate it, except now we're back to my original question. Don't we need to know the number of moles? Yeah. So I'm going to need to get the number of moles here. So I'll do that in a second, yeah.
Did you say we use CP instead of CV for that equation? No. This will only work for CV. The Q will need to use either the CV or the CP, depending on what process it is. So the CV goes with the Q only during constant volume. The CP goes with the Q only during constant pressure. So that's the difference of those processes. And the Q for the adiabatic is 0. The Q for the isotherm, is negative of the work because there's no change in temperature. And the work is the integral of negative P dV. And so the negatives cancel off, and the P can be written as nRT over V dV, and so nRT natural log of final volume over initial volume. Okay, so again, the Q depends on what process. Constant volume, constant pressure, adiabatic, isothermic. But the E does not. So we'll come back to those to fill in this in just a second. But I'm looking at this column because I have this. All right, so I will fill this in, but I will start with N.
And I need to know the pressure, volume, and temperature somewhere, and I know them everywhere, so that won't be hard. But I'll just use at A and grab a calculator here. The pressure, they say, is 1 atmosphere. And I'm going to go ahead and change it into pascals. Only because I know R is 8.31 joules per mole per Kelvin. And since I have it memorized in the joules, I better make sure my units match up there. If you do it in atmospheres and liters, would you 0.082? Okay, I don't even want to confuse that in my brain there. It's going to mess me up. Those crazy chemists with their silly units, you know. All right, so I'm going to stay away from those atmospheres and liters and use real units. No, use use pascals. And so pascals come out to be joules. So I'm going to convert my atmospheres into pascals. And I'm going to convert my liters into cubic meters. And fortunately, that's just a factor of 1,000. So there is 1,000 liters in a cubic meter. So this just becomes 0.004. And then the temperature, what did we say over there? 300? 300 Kelvin. So again, this Pascal times that cubic meter makes a joule, so the joules will cancel off. This 300 Kelvin will cancel off, and so we are going to be left with moles. How many moles? All right, so getting my calculator, it's 101,300 times 0.004. Divide that by 8.31, divide that by 300, and we are looking at 0.16, and I'll just round to a 3 moles for N. So that's how many moles I have to work with. And like I said earlier, the reason that is very helpful is that I can find all these energies right here. Okay? And so, looking at A to B, I would have N CV delta T. So N is 0.16, did I say 3? 3 moles. Again, want to think about this. CV, what kind of gas is it? Diatomic. So how many degrees of freedom do I have? 5. So CV is what? 5/2 R. Good. Change in temperature. Now, that would be final, which is B, minus initial. So the final is 900, and initial is 300. Now, I should probably ask, before I even do the calculations, it's going to be a positive number or a negative number? Positive, right? You can see 900 is bigger than 3, and it comes out to be positive. And hopefully that matches. Why would I expect it to be a positive number? Yeah, how am I going to make the pressure go up without changing the volume? Yeah, making the molecules go faster, right? Putting energy into it, heating it up, right? And we said energy in is a positive number. And so getting my calculator, 0.163 times 2.5 R times 600 comes out to be 2,032 joules. And so that's how much energy in joules need to be added to that gas. Yeah.
So for B to C, we could use the same NCV delta T, except for our delta T.
Exactly. So B to C would be 0.163, 5/2 R. The final temperature is now at C, 660. Initial temperature is 900. And I should ask, positive number or negative number? Negative, right? Which hopefully makes sense. Why negative? Well, yeah, of course, one answer is the temperature goes down here, right? And I expect the internal energy to go down because it's doing work on the environment. Why the internal energy goes down. I'm not putting any heat into it, and I'm taking energy out of it as work, so the total energy inside gets less. And so I expect a negative number here. And sure enough, that's going to give me a negative number. So again, 163 times 2.5 times 8.31 times 660 minus 900 will give me a negative 813 joules.
Is that equal to delta T, you say?
Yeah, so that's delta T. From B to C. C, final, minus initial.
Where are you getting that number at? Because you're getting it from that equation, right?
What number? Yeah, that's why. Yeah.
What is your R unit?
R is 8.31 joules per mole per Kelvin. It'll never change. It's called, that's the constant.
The work for B to C is going to be the same number, right?
Good question, but let me hold off on that one. Let me, since I'm working on this chart, I'll do this one. But you're right, you see the puzzle. I could go this way just as well, right? But hopefully not to confuse people, let me finish right here. Couldn't I do the same math here? Or, don't I know that these three have to add up to 0? So nothing better than having two options, right? I only got to see one, and I can check my work. I will tell you then, you will find on the test that you will know right away how you did. Because you get to this point, you've got two ways, and you can check your work, and it either works or it doesn't. Okay? And most people, of course, when they realize it doesn't work, sit there and get it right till they get it work. So hopefully that will happen to you. You'll go, oh, I did it wrong. Fine. I still got 20 minutes left in the test, and I'm going to fix it. Right? And so check this. So let's see what happens. I'll go ahead and put the next one in here, which would be C to A, 0.163, 5/2 R. And then I'm going to go final, which is 300 minus 660. Again, not a surprise, it's a negative number, right? Should come out to be a negative number because I am going from here to here. I am getting heat out of, or I'm slowing it down. I am taking the energy out of them. So 0.163 times 2.5 times R times a change in temperature of 300 minus 660, coming up to be a negative 1219. And I hope then that when I put these three together, I get 0. Yay! Feeling good about that one, right? Now, you mentioned at this point, especially here, what was nice about the B to C? Yeah, the Q is 0, so we can fill that one in right away. And then, of course, once you know these two, what do you know once you know two of them is you know all of them because these two added together are that one. So what would you say about the work here? Yeah, that's a negative 813. Exactly, yeah. No, it should be negative. And we should ask, does that fit my physical picture here? It's doing work on the environment. It's pushing the environment. It's losing energy. So this should be negative, and that should be negative. Those two add together should be that one. Perfect. Right? All right. A to B is fairly easy. What do you know about A to B? Constant volume. So what does that help you with? The work should be 0, right? There's no work done on the environment. So that one's 0. And that should help because these two have to add to that one. So what are you saying about the heat added? Right? And maybe I should check it. Because isn't this a constant volume one? So couldn't I get it right here? Which, of course, is the same thing I calculated back here. So yeah, it does match. Yay, okay, won't even check. Right? All right. How about the C to A?
Work is negative 2.
Okay, the work here I could calculate. But I could also do the Q. Because isn't the Q a constant pressure? All right, but then also I don't need both methods because once I know one, I can find the other. So I'll tell you what, let's try both of these calculations and see if they don't, both of these calculations, see if they don't add up to that one, right? So I'll start with the Q. The Q would be over here. It would be a 0.163. What would CP be? Diatomic? 7 halves are, exactly. And what are we going from C to A? So we're finishing at A, so that's 300 minus 660. So according to this, 0.163 times 7 divided by 2 times 8.31 times 300 minus 660 comes out to be a negative 1,707. And again, I think it fits my tuition here, right? I should be cooling it down. I should be taking heat out of it. But of course, you'll notice the magnitude of this number is a little bit more than that, and that kind of makes sense because you have to take more heat out than the change in internal energy because the gas is also getting work done on it as it's compressed. And so the change in internal energy is not as big as the energy you took out of it because energy is going into it as you're compressing it, which is what this number is going to come to be. As you said, I can calculate the work. Work would be A minus P delta V. So during this process, I have a pressure of 1 atmosphere. And again, for things to come out in joules, let me put that as pascals. Okay? And so there's my pascals. And then my change in volume is final volume, which is 0.004 minus 0.0088 and cubic meters. So that my work will come out in joule. And of course that's a negative and that's a negative. So it's going to come out to be positive, 101,300 times 0.004 minus 0.0088, close bracket. And this is 486. So 486. There. And a positive number. And then if I go 1707, do I get 1219? Well, I get 1220, 1221. All right. So other than some rounding there, I'm on shot. So good. I'm feeling comfortable about them. And now I think I can finally answer the question here. What they want, the total work. So I can add all these or I can add all these, right? And of course, they better add to be the same number but equal in sign so that they give me a 0 right there. And so this one is 486 minus 813 means it's a negative 327. And so the 2032 minus the 1707 hopefully is a plus. And it looks like I'm off by 2 after some rounding. But accepting my rounding as a less than 1% error, they seem to match. So perfect. These two are equal and opposite, give me 0. My work is a negative number, meaning what?
You're doing
Yeah, I'm doing work on the environment I have put heat into. And so this makes what we're going to call in the next chapter a good heat engine. I put heat in and I got work out. I burnt the gasoline, car is now moving. Right? And so that's what those numbers tell me. Oh, and that took a little longer than I anticipated. I wanted you to see a bunch, but I wanted you to also see that one. All right. But that, huh? Yeah, but I think that had a little bit of everything. It did not have the isotherm process in there. And so 39 does. in fact, 39, I like it. I don't think we'll have enough time to maybe look at all of them again. But 39 doesn't have a closed cycle. What it does have, though, is a chance to look at all 4 cycles separately and independently. And so here's what it says here in 39. It says an internal energy function is given by this equation. So they have E equaling 7/2 nRT. So that means we have 7 degrees of freedom. So as you saw there, this could have been a diatomic that was at 1,000 Kelvin or higher, because we have to have more degrees of freedom than just our 5 degrees of freedom. Or it could be a more complex molecule, not sure. And it doesn't really matter once I know this relationship. It just says the internal energy is described by this function. It then says a 2 mole sample of gas starts at 1 kilopascal and 300 degrees. So maybe if I put a PV diagram up here, hint, hint, always start with a PV diagram, right? And I will start by putting a little dot right. Well, maybe I'll put it more in the middle because I'm not sure what they're going to ask me to do here. Okay, but I'll put the dot there, and they say the pressure is 100 kilopascals and the temperature is 300. So I'll put a 300, and I'll put 100 pascals. Yeah, do you want me to stay in kilopascals or? Okay, so 100,000 pascals, so 100, which is roughly 1 atmosphere, and so it's 300. So this, sounds like a gas at regular room temperature. You just have it sitting in a container. Now you're going to do something with it. They do say you have 2 moles. Then it goes on to say, for each of the following processes, determine the final pressure, the final volume, and the final temperature. Also, the change in internal energy of the gas. Okay? The energy added to the gas by heat and the work done by it. So again, we're going to do something with it. We're going to start maybe at point A, and point A will have a pressure, a volume, and a temperature. And we're going to go to point B. And in this process from A to B, they are asking you, what is the change in internal energy? What is the heat? And what is the work? And so it's not a whole cycle, but it's a good problem to go through all 4 options here. Because here's what they said. They say, we'll start with the gas and we'll do this. Let's say A, the gas is heated at a constant pressure to 400. Okay, so constant pressure. What would that look like? Right? That's how I would describe it, right? From A to B. So starting at A, I would have a pressure of 100,000 pascals. I would have a temperature of 300. They don't originally tell me the volume, but it's probably worth coming over to here and saying volume is equal to nRT over P, right? Because they did tell me I have 2 moles. R is 8.31, the temperature is 300, and the pressure is 100,000. And so indirectly, they did tell me the initial volume. And so I would have a 2 times 8.31 times 300 divided by 100, 1, 2, 3,000, coming up with a volume of 0.0499 if my volume is in cubic meters and my pressure is in pascals and my temperature is in Kelvin. Or if you like liters, that would be 49.9 liters. Move the decimal 3. So that's my starting conditions. And what they're saying now is warm it to 400. All right, well, like I said, this is one of the ones we really already covered, so I want to make sure I get to the isothermic one here. But this is the isobaric. So what is your pressure going to be? Yeah, still going to be the same pressure. So what's your volume? Well, that's where this comes into play, right? It's going to be the same math, it's just now we're going to have a 400 up there. So it's 2 times 8.31 times 400 divided by 100, 1,000. And this should now be at a volume of 0.0665. Yeah.
The number of moles was given to us, right?
Yes, and the number mole was given. I know I went kind of fast there. But again, probably the most important thing I wanted to show you today is the chart, right? I think the chart really helps a lot. Both charts, a chart listing the energies that are going on and a chart listing the state of the gases, okay? And then you can stand back and look and say, is this the ideal gas law? Is it isobaric? Is it? What equation would be appropriate under that condition? Now again, I think the best one to focus on is right here, because if you know CV, you got it. And in fact, in this problem, they gave me one deliberately that was out of the normal so that I wouldn't just fall back on something I've done in the past and said, this is the change in internal energy. So as I use this equation right here, the change in temperature is 400 to 300. So putting those numbers in, I have 7 divided by 2 times the number of moles, 2, times 8.31, times a change in temperature of 100. And so they have given me the easy way out here by saying this is 5,817. I think they've also given me a nice easy way out to get the work. Because what kind of process is it? It's isobaric here. So it's minus P delta V is what the work comes out to be for the constant pressure. And so the pressure here is 100,000 pascals. The final volume is 0.0665 minus 0.0499. And again, a negative number. Since the gas is getting bigger, it's doing a negative on the environment here. So 123 times 0.0665 minus 0.0499, coming out to be 1,660. So 1,660 when measured in joules. So that's how much work. Negative number, sorry. Negative. I forgot to put the negative in my calculator there, but positive with a negative makes a negative. And it should be, it's expanding here. Okay, which then means I could get this one, right? Because if I take this number, 5,8, how are we doing on time? 1,7, and subtract a negative 1,660, that means we've added 7,477 joules of energy to get it there. Okay? So we added that much heat, although we lost some energy because the gas expanded. That's why it only had a total change of internal energy of this, and that's why the temperature only went up 100 degrees instead of more. Real quickly then, it says, well, what if instead of warming it to 400 at constant pressure, you warmed it to 400 at constant volume? All right, so what would change here? Yeah, well, maybe I should start. The starting conditions is going to be the same, but then this would be the new volume, which means the pressure would be different. And so using pressure as nRT over V, I should be able to get the pressure. So again, see how I use the ideal gas law to kind of fit in these pieces here. So it's 2 moles times 8.31 times a temperature of 400 divided by a volume of 0.0499, coming up with 133,226 pascals for the pressure here. And then how would that change over here? All right, big thing I want you to catch is delta T is still the same. So when you go to calculate it in here, isn't the change in internal energy just related on temperature? And so that number is still going to be the same. What was it, a 13?
No,
17? Accidentally erased it. But this one hopefully is easy. What's the work? 0. So what's the? Yeah, so that's going to be a negative.
Wait, no, just
A positive. Yeah, thank you. I believed you. You said negative, so I went for it. No, but it's positive, right? And where it can make sense. Positive, I'm going to add energy to it as it goes up. All right, well, and then the one I really wanted to get to in this, I'm going to do it real quick here, is what if the gas then, where does it have it here? The gas is compressed at a constant temperature. So here's the isotherm. Until the pressure becomes 120 kilopascals. All right, so we're starting here again, but now we are compressing the gas until we get to 120. And so this is my isotherm. Okay, well, I guess we would have the same starting conditions. What would be different here? Well, pressure goes to 120, that's given. Volume I don't know. Temperature I do though. What's temperature? 300. And so that was the key to the problem, is this is an isothermic process. Same temperature. And of course, once you know those two, you can get the volume. I'm out of time here, but I'll jump over to here then. What would happen to here?
Energy is 0.
Yeah, that's the key part of this. Maybe we should call it the Rosetta physics there. I mean, when you got that one, you know this and you know this. And then if you know either one of these, you can get this. And I claim we can get these. I did them over here, so we're out of time here, but this was the isotherm. Q is equal to the negative of W. Since it is a constant temperature, replace P with nRT dV, and so this would be the equation to get the Q. And for that matter, the W. They would just be opposite in sign. So I can fill that in, and I can fill that in. All right. Well, good luck on the homework. And take a good look at 22 before you come on Thursday, so we can get into the second law of thermodynamics and finish up our